There is a moon in our solar system that should not exist. It is small, barely 500 kilometers wide. A pale, cracked marble suspended in the rings of Saturn, so distant from the sun that its surface temperature hovers at -201 degrees Celsius, cold enough to freeze nitrogen, cold enough to shatter steel like glass, cold enough to make the vacuum of deep space feel almost warm by comparison. It should be dead. Every law of planetary physics says it should be dead, and yet something is alive inside it. Not metaphorically, not in the poetic sense that scientists sometimes use when describing dynamic geological systems or interesting chemical gradients. Something is happening inside Enceladus that has forced researchers, serious, measured, career-defining researchers, to sit in silence after reviewing their data. Something that has caused entire teams to recheck their instruments, recalibrate their sensors, and rerun their calculations not once, not twice, but dozens of times. Because the alternative, accepting what the numbers are actually saying, is almost too significant to speak out loud. This is that story. Enceladus is not famous in the way Mars is famous. It does not carry the romantic weight of Europa or the atmospheric drama of Titan. It is, in most casual astronomical conversations, a footnote. One of Saturn's 80-plus moons, notable mainly for its reflective surface, which bounces sunlight so efficiently that it glows like a white eye in the darkness of the outer solar system. But the Cassini spacecraft changed everything. When Cassini swept past Enceladus in 2005, its instruments detected something that triggered immediate alarm among mission scientists. Plumes, enormous, continuous geysers erupting from the moon's south polar region, jets of water vapor and ice particles blasting hundreds of kilometers into space at speeds exceeding 1,400 kilometers per hour. Not a trickle, not an anomaly. A sustained, violent, continuous eruption of material from beneath the surface, forming Saturn's E-ring with debris from a world that, by every prior model, should have been frozen solid billions of years ago. The question was not just what was happening. The question was how. There is no sufficient tidal heating mechanism to fully explain what Cassini found. The gravitational interaction between Enceladus and its neighboring moon Dione is real, and it generates heat. But not enough. Not nearly enough. The energy output from the south polar region of Enceladus is estimated at approximately 15 to 26 gigawatts. A staggering thermal output for a body that small, in a location that cold, receiving that little sunlight. For reference, that is more heat than all the geothermal energy released along the entire length of the mid-Atlantic ridge on Earth. From a moon smaller than the state of Arizona. Something is generating that energy. And what was found inside the plumes, the chemical composition, the molecular signatures, the specific ratios of compounds erupting from that hidden ocean, is what made scientists pause in a way that no press release has ever fully captured. Because what Cassini tasted in those plumes was not just water. It found silica nanoparticles, microscopic grains that only form at specific temperatures and pressures, at hydrothermal vents on the ocean floor, where superheated water meets rock and mineral reactions occur that are, on Earth, inseparable from one thing: life, not life itself. That distinction matters enormously and must be held carefully. But the chemical conditions, the precise environmental fingerprint, the temperature gradients, the pH levels, the presence of molecular hydrogen, produced when water reacts with rock in a process called serpentinization. A process that on Earth feeds entire ecosystems in the complete absence of sunlight. Deep beneath the ocean in environments we once thought were too extreme for biology to exist. Enceladus has all of it, every single prerequisite. Liquid water, confirmed. An energy source, confirmed. Organic chemistry, confirmed. Complex carbon molecules, detected. Phosphorus, detected. The 6 elements considered essential to life, as we understand it. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all present, all erupting continuously into space from an ocean that has existed by some estimates for billions of years, an ocean no sunlight has ever touched, an ocean sealed beneath kilometers of ice, kept liquid by forces we do not yet fully understand, churning in the darkness at the bottom of a world that orbits a gas giant 1.5 billion kilometers from the sun. And the scientists who stared at this data, who spent years validating these findings, checking and rechecking and publishing and defending. Some of them have said carefully, in the measured language of peer-reviewed journals and academic conference rooms, that they cannot rule out biology. They cannot rule it out. That sentence, small, controlled, almost bureaucratic in its restraint, is one of the most consequential sentences ever written in the history of human exploration. Because to not rule something out in science is not a casual dismissal. It is an acknowledgement that the evidence does not exclude the possibility, that the data is consistent with the hypothesis, that the universe, which we have long imagined to be vast and cold and empty, may have placed something living, something metabolizing, something consuming, something existing inside a frozen moon in our own backyard. And we have only just begun to understand what we found. Consider what it means to find water where water should not exist. Not on the surface, not in a thin atmospheric vapor, not in frost deposits scattered across a crater rim, but liquid water, vast, deep, salt-rich, chemically active liquid water, sealed beneath the frozen crust of a moon so far from the sun that the star itself, seen from that distance, would appear as nothing more than an unusually bright point of light among millions of others. Smaller than a full moon looks from Earth. Cold, distant, indifferent. Water, in the human imagination, is life. Every religion that ever emerged from a desert understood this instinctively. Every civilization that survived antiquity built itself along a river. Water is not merely a resource. It is the condition of possibility itself. The molecular architecture that allows chemistry to become biology, that permits compounds to dissolve and react and reorganize, and eventually, over vast timescales, to begin doing something that resembles intention. And Enceladus has an ocean larger than some seas on Earth. The numbers are difficult to hold in the mind without losing their weight. Beneath a shell of ice estimated between 19 and 25 kilometers thick at the poles, and thinner, dramatically thinner, perhaps only a few kilometers, near the south polar terrain, there exists a global ocean of liquid water. Not a lake, not a subsurface reservoir, a global ocean wrapping entirely around the rocky core of the moon, churning in perpetual darkness, subject to tidal forces that flex and compress the ice shell above it like a living lung, breathing in geological time. The ocean has been there for a long time, possibly for billions of years. Think about what a billion years means in biological terms. Life on Earth, in its most primitive microbial form, required only a few 100 million years to emerge after the planet's ocean stabilized. A billion years is enough time for single-celled organisms to diversify into thousands of metabolic strategies. enough time for biology to solve the problem of photosynthesis or chemosynthesis, or any number of energy harvesting mechanisms we may not yet have names for. A billion years of liquid water, mineral-rich rock, thermal gradients, and organic chemistry is not a dead system waiting to be discovered. It is a laboratory that has been running unsupervised for longer than complex life has existed on Earth. The hydrothermal vents at the floor of this ocean, and there must be hydrothermal vents, the silica nanoparticles found in the plumes leave no serious alternative, are not passive features. On Earth, deep-sea hydrothermal systems are among the most biologically productive environments on the planet. Per unit area, they support tube worms over 2 meters long, ghostly white crabs, chemosynthetic bacteria that form the base of entire food webs, fish adapted to pressures that would crush a submarine's hull. None of them have ever seen sunlight. None of them require it. They live entirely on the chemical energy released when superheated water interacts with rock, the same process occurring right now at the bottom of an ocean on a moon of Saturn. This is not speculation. The molecular hydrogen detected in Enceladus's plumes is the smoking signature of serpentinization, the geochemical reaction in which water percolates through olivine-rich rock, oxidizing iron and releasing hydrogen as a byproduct. On Earth, molecular hydrogen produced by serpentinization is consumed by microorganisms called methanogens, some of the oldest life forms we know of. Organisms whose lineage predates the existence of atmospheric oxygen, creatures that have been metabolizing hydrogen and carbon dioxide into methane since before the first animal drew a breath. Methane was also detected in the plumes of Enceladus, in quantities that cannot be fully explained by known abiotic chemistry alone. The researchers who published this finding in peer-reviewed journals, subject to the most rigorous scrutiny modern science applies to extraordinary claims, did not say that life is present. They were careful, precise. The language of science requires a particular discipline around absence of certainty, but they stated clearly that known geochemical and hydrothermal processes alone are insufficient to account for the observed methane concentrations. That biology, specifically methanogenesis, cannot be excluded as a contributing source. Cannot be excluded. There is a philosophy of discovery embedded in that phrase that most people walk past without stopping. Science, at its frontier, does not prove. It eliminates. It builds a wall of impossibilities around a question and measures what remains standing when the wall is finished, what remains standing in the case of Enceladus. After decades of data collection, instrument calibration, competing hypothesis testing, and international peer review, is the possibility of living organisms metabolizing in an ocean on another world. That wall has not eliminated biology, and the implications of that failure to eliminate are staggering in a way that is difficult to communicate without sounding theatrical, except that the theater, in this case, is the universe itself, which has no interest in understatement. If life exists in the ocean of Enceladus, it did not originate from Earth. There is no plausible vector by which terrestrial biology could have seeded that moon, which means life, should it be present, arose independently, separately from the same raw materials, under different conditions, on a different world, around the same star. And if it arose twice in one solar system, the mathematics of that become almost immediately verifiable as a principle rather than an accident. Twice is not a coincidence. Twice is a rule. If life emerges wherever liquid water, chemical energy, and organic molecules coexist for sufficient time, And those conditions are now known to exist in our solar system, not only on Earth, but potentially on Enceladus, on Europa, possibly on Titan, in a radically different chemical framework. Then the universe is not a sterile expanse, occasionally interrupted by biology. The universe is a medium in which biology is a natural outcome, a tendency, a pattern, and the silence of the cosmos, which has always felt vaguely reassuring. A silence that allowed us to believe we were special, singular, uniquely conscious in an otherwise mechanical universe. That silence changes its meaning entirely. It stops sounding like absence. It starts sounding like patience. There is something almost unbearable about that reframe. Humanity has spent millennia constructing cosmologies that place consciousness at the center, not always literally, but architecturally, in the sense that our stories about the universe have always assumed that the universe is the backdrop, and we are the event, the stage and the play, the darkness and the light. Every theology, every secular humanism, every philosophical tradition that grants primacy to the human experience, all of them rest, at some level, on the premise that awareness is rare, that we are exceptional. Enceladus does not care about that premise. Its ocean churns in the dark regardless of our cosmologies. Its vents exhale hydrogen into pressurized water regardless of what any civilization on any planet has decided to believe about its own importance. The chemistry proceeds on its own schedule, in its own silence, without waiting for permission or observation or philosophical frameworks to accommodate it. This is what the data is actually saying, beneath the careful language and the calibrated uncertainty. The universe makes life. Not here, not there, not occasionally, but wherever the conditions align, and the conditions align more often than anyone was prepared to admit. The chemistry trends toward complexity, toward metabolism, toward replication, toward something that, by any working definition, is alive. Enceladus is not a discovery about a moon. It is a discovery about what kind of universe we are living in. And that discovery, incomplete, contested, thrilling, terrifying, is only just beginning to reveal its full dimensions. There is a particular kind of scientific courage required to send a machine to die. Cassini, the spacecraft, the mission, the 17-year odyssey that became one of the most consequential acts of exploration in human history, was not built with an exit strategy. It was built with a purpose, and when that purpose had been fulfilled, when its fuel reserves dwindled and its instruments had gathered more data than any team of scientists could fully process in a generation, the decision was made deliberately, coldly, and with full awareness of what was being sacrificed. On September 15, 2017, Cassini was aimed at Saturn and destroyed. Not abandoned, not decommissioned, destroyed, plunged into the atmosphere of the gas giant at speeds exceeding kilometers per second, burned to atoms, erased from physical existence in a controlled act of terminal science. The reason was Enceladus. Specifically, the reason was the possibility that Cassini itself had become a contamination risk. That its hull, no matter how carefully sterilized before launch in 1997, might carry dormant terrestrial microorganisms capable of surviving the vacuum of space. And if Cassini were allowed to drift uncontrolled and eventually impact Enceladus, those organisms might reach the ocean beneath the ice. They might contaminate the very thing humanity most desperately needs to examine in its original, unaltered state. The decision to destroy a $6 billion spacecraft, a machine of extraordinary scientific productivity, still functioning, still transmitting, still capable of years of additional observation, in order to protect the biological integrity of an alien ocean on a distant moon. That decision contains within it an entire philosophy. It says, we believe something might be alive in there. It says, we take that possibility seriously enough to sacrifice our most powerful tool of investigation rather than risk corrupting the answer. No space agency destroys a functioning spacecraft casually. The planetary protection protocols that mandated Cassini's fate are not bureaucratic overcaution. They are the institutional acknowledgement, encoded in international space law, that the solar system may contain life, and that humanity's obligation to that possibility outweighs the operational convenience of keeping its machines running. Let that sink into its full depth. An international legal framework, ratified by the major spacefaring nations of Earth, exists specifically to protect extraterrestrial life from contamination by human technology, not theoretical future life on hypothetical exoplanets. Life that might exist right now in our own solar system, close enough that a spacecraft we launched in the last century already passed through its exhalations. Cassini flew through the plumes of Enceladus directly, multiple times. It tasted them with mass spectrometers and ion and neutral mass analyzers and cosmic dust analyzers. Instruments of almost incomprehensible sensitivity, capable of identifying individual molecular species and gas concentrations so thin they barely register as matter. And what those instruments returned, pass after pass, flyby after flyby across years of accumulating data, was a portrait of an environment so chemically rich, so thermally active, so precisely configured for the emergence and sustenance of microbial life, that the scientists who spent their careers analyzing the results have said, repeatedly, that Enceladus is the most promising place to search for life beyond Earth. Not promising in the vague, hopeful sense of a term stretched to cover ambiguous data. Promising in the rigorous sense, meaning that the known prerequisites are confirmed present. That no known law of chemistry or physics precludes the existence of organisms there. And that the observed data contains signatures consistent with biological processes that cannot yet be fully explained through abiotic mechanisms alone. The plumes themselves are a kind of miracle of access. Consider what they represent. Enceladus has given humanity something that no other world in the solar system has offered. A direct, continuous sample of material from a subsurface ocean erupted freely into space, requiring no drilling, no landing, no excavation through kilometers of ice. The ocean is broadcasting itself. Every second of every day, approximately 200 kilograms of water vapor and ice particles and organic compounds and molecular hydrogen and complex carbon molecules are ejected from the south polar terrain of Enceladus into the vacuum of space, forming a plume system visible from millions of kilometers away. It is as if the ocean is trying to be found. The specific compounds identified in those plumes read like a checklist assembled by an astrobiologist designing a habitable environment from scratch. Water, the universal solvent, the medium in which carbon chemistry becomes infinitely more flexible and reactive. Molecular hydrogen, a direct energy source for chemolithotrophic organisms, life forms that eat rock chemistry rather than sunlight. Carbon dioxide, the carbon source that methanogens combine with hydrogen to produce methane and energy. Ammonia, a nitrogen source critical to the synthesis of amino acids and nucleotides. Silica nanoparticles, the crystalline proof of hydrothermal activity at temperatures between 90 and 110 degrees Celsius, a range entirely hospitable to thermophilic life. Complex organic molecules with masses exceeding 200 atomic mass units. large carbon-rich compounds that on Earth are associated with biological or pre-biological chemistry. And methane. Always the methane. In concentrations that the models cannot account for. In quantities that exceed what the known geochemistry of the system should produce. The methane anomaly in the Enceladus plumes is not a minor discrepancy. It is a persistent, reproduced, published scientific problem that has resisted explanation for years, and for which methanogenic biology remains one of the most viable hypotheses on the table. Here is the analogy that captures the weight of this properly. Imagine you are an archaeologist excavating a sealed room that has been closed for 1,000 years. You open the door, and the air that rushes out contains wood smoke, bread, the trace of candle wax, the chemical signature of fermentation. You have not yet seen the room. You cannot yet confirm that people lived there. But the chemistry of the air is not consistent with an empty space. It is consistent with occupation, with activity, with presence. That is the smell of Enceladus's plumes. Not proof, not confirmation, but consistency with presence. A consistency that has survived every attempt to explain it away through simpler, lifeless mechanisms. What Cassini proved, definitively and without scientific controversy, is that the conditions for life exist in our solar system beyond Earth. That is already an epical statement. That alone, the confirmation of a second habitable environment, even if currently uninhabited, restructures the probabilistic landscape of the universe in ways that ripple outward without limit. Because habitability is the threshold. Once you confirm that the universe routinely creates habitable environments, and Enceladus is now one of at least 4 or 5 strong candidates for habitability in our solar system alone, the question is no longer whether life could exist elsewhere. The question becomes, given that the conditions are met, what is the probability that they remain sterile? And that probability, when examined honestly against the 4-billion-year history of biology on Earth, is not reassuring to anyone invested in the uniqueness of terrestrial life. On Earth, every habitable environment eventually gets colonized. Every thermal vent, every acidic hot spring, every subglacial lake beneath kilometers of Antarctic ice. If there is liquid water and a chemical energy source in sufficient time, something is living in it. Life does not politely wait for favorable conditions and then decline the invitation. Life on this planet is aggressive in the most fundamental thermodynamic sense. It fills available niches because doing so is energetically favorable, because biology is, at its core, chemistry that has learned to perpetuate itself. Enceladus has been habitable by everything we understand about habitability for potentially billions of years. The invitation has been standing for a very long time. And Cassini, in its final years, pressing its sensors into those plumes with the determination of a machine that knew it was running out of time, handed humanity the evidence that something may have RSVP'd. Whether we are prepared for that answer is a different question entirely, and one that science, for all its precision, cannot answer for us. Science does not panic the way people panic. There are no raised voices in the control rooms. No one overturns a table or runs down a corridor. The panic of science is quieter, more methodical, and in many ways more profound, because it expresses itself through the one behavior that scientists are trained, above all else, to avoid: rechecking work they already trust. When the Cassini data on Enceladus's plume chemistry began returning results that suggested conditions inconsistent with a purely abiotic system, the first response was not publication. It was not press conferences or cautious public statements about the implications of the findings. The first response was silence. The particular, concentrated silence of a room full of people who understand exactly what they are looking at and are not yet willing to say it out loud, because saying it out loud transforms it from a private anomaly into a public claim. And public claims carry consequences that private anomalies do not. They rechecked the mass spectrometer calibrations. They reanalyzed the instrument sensitivity curves. They modeled alternative geochemical pathways that might produce the observed hydrogen and methane ratios without requiring biology. They consulted with geochemists who had no prior investment in the Cassini mission, asking them to stress test the data from outside. They ran the numbers again and again, and when the numbers kept returning the same answer, when every alternative explanation either failed to account for the full data set or required physical conditions more exotic than biology itself, they began, carefully, to write. The resulting papers are studies in disciplined understatement. They use phrases like "not inconsistent with" and "cannot be ruled out," and "consistent with, but not limited to, biological sources." They are written in the passive voice of institutional caution, every sentence hedged against overinterpretation, every conclusion bracketed by the acknowledgement of what remains unknown. And yet, read carefully, read by someone who understands that scientific language compresses its most explosive content into its most measured phrases. They say something that should have restructured the conversation of every civilization on this planet. They say, "We found what life needs, producing what life produces in quantities that life alone can fully explain. The methane anomaly is the center of this story, and it demands specific attention. Thermodynamic modeling of Enceladus's hydrothermal system, the best models available, built on decades of Earth-based research on deep-sea vent chemistry and constrained by the precise measurements Cassini returned, predicts a certain level of methane production through abiotic processes. Serpentinization produces some methane. Thermal decomposition of organic compounds produces some methane. The degassing of primordial carbon trapped in the rocky core produces some methane. Add all of these together, weight them by the estimated temperatures and pressures and reaction rates in the Enceladus hydrothermal system, and you arrive at a number. The observed methane concentration in the plumes is significantly higher than that number. Not marginally, not within the range of instrumental error or modeling uncertainty. Significantly. Enough that when researchers published their analysis in the journal Nature Astronomy, they stated explicitly that the data suggests either the presence of biological methanogenesis or geochemical and geophysical processes unlike anything observed in any studied environment on Earth. In other words, either something is alive down there, or Enceladus is operating by rules of chemistry and physics that we have never encountered before and do not yet understand. Both options are extraordinary. One of them is far more extraordinary than the other. Consider the specific organism that keeps appearing in this scientific conversation, because its appearance is not accidental. Methanobacteriales, the order of microorganisms known as methanogens, are among the most ancient life forms on Earth. Their metabolic pathway predates the Great Oxidation Event, that catastrophic moment approximately 2.5 billion years ago when photosynthetic bacteria flooded Earth's atmosphere with oxygen and triggered a mass extinction of anaerobic life. Methanogens survived because they do not need oxygen. They never needed it. They live in environments where oxygen is absent or toxic, deep sea vents, hydrothermal systems, the digestive systems of animals, the sediments of lake floors, They consume molecular hydrogen and carbon dioxide. They produce methane and water. They require no sunlight. They require no surface. They require no atmosphere. They require only what Enceladus has in apparently abundant supply, in an ocean that has been stable for potentially billions of years. Sealed from every surface perturbation, insulated from the radiation environment of space, heated from below by a rocky core whose thermal activity shows no signs of cessation. Methanogens on Earth have been found in environments so extreme that their discovery forced a complete revision of what habitable means. They have been recovered from rocks drilled 3 kilometers below the surface of South Africa, living in water that last saw the surface over 20 million years ago. They have been found in subglacial lakes beneath the Antarctic ice sheet, in temperatures near freezing, in darkness so complete that the concept of a day-night cycle has no meaning to them whatsoever. They are, in the deepest sense, creatures of Enceladus-like conditions. The analogy that forces itself forward here is almost too precise to be comfortable. Imagine that you are studying an ecosystem you cannot yet access directly. A sealed vault beneath the ground, inputs and outputs measurable only through a narrow vent that opens periodically to the surface. You measure what comes out of the vent. You find water vapor, molecular hydrogen, carbon dioxide, complex organics, and methane in quantities your models of the vault's known chemistry cannot fully account for. On Earth, in every analogous system ever studied, the explanation for that excess methane has always been the same. Something is eating the hydrogen. Something is breathing out methane. Something is metabolizing. The panic, the quiet, methodical, instrument rechecking panic of the scientific community, is rooted in the recognition that the same logic applies, consistently and without obvious exception, to Enceladus. And that recognition carries within it a second, deeper terror that the first one conceals. If microbial life exists in the ocean of Enceladus, it has been there for a very long time. Long enough to evolve, long enough to adapt to its specific chemical environment with the ruthless precision that natural selection applies over geological timescales. Long enough, potentially, to have diversified the way Earth's hydrothermal vent communities diversified, the way every stable habitable environment on this planet eventually produces not one species, but entire ecosystems of interdependent organisms, each occupying a metabolic niche, each modifying its environment in ways that create new niches for others. Life does not stay simple if it has time to become complex. And the ocean of Enceladus has had time that staggers the imagination. This is the implication that scientists are most careful not to voice in public forums, because it crosses the boundary between what the data currently supports and what the data, if extended by reasonable biological analogy, suggests. But the boundary between confirmed evidence and legitimate inference is not a wall. It is a gradient. And along that gradient, the question of what 4 billion years of unchecked biological evolution in a sealed, resource-rich, thermally stable ocean might produce is not a frivolous speculation. It is the next logical question. The Cassini mission was never designed to answer it. Its instruments were extraordinary for their time and purpose. But detecting complex multicellular life, or even detecting the chemical signatures of a biologically diverse ecosystem rather than simple chemosynthetic metabolism, was beyond what a fly-by mission with mass spectrometers could reasonably achieve. Cassini found the fingerprints. It could not see the hand. What it handed humanity in 17 years of immaculate data collection and one final act of deliberate self-destruction was the clearest possible argument for returning, For going back to Enceladus with instruments designed not merely to detect the prerequisites of life, but to look directly for life itself. To sample the plumes with technology capable of identifying cellular structures, nucleic acids, isotopic biosignatures, the molecular machinery of metabolism at the scale of individual organisms. That mission does not yet exist. It is being proposed. It is being argued for in papers and congressional budget hearings and International Space Agency planning documents. It is being advocated for by scientists who have spent their careers sitting with the Cassini data, living with the anomaly, understanding in a way that a summary cannot fully convey how urgently the question demands a direct answer. Because the alternative, leaving the question open, maintaining the careful ambiguity of cannot rule out while possessing the technological capability to do better, is its own kind of choice. And it is not a choice that history will judge kindly. Every generation of scientists inherits a set of impossibilities, not failures, not gaps in knowledge that patience and funding will eventually close. Impossibilities. Hard boundaries drawn by the best available evidence, defended by the most rigorous theoretical frameworks, taught to students as the settled shape of reality. And every generation, without exception, watches at least one of those impossibilities quietly dissolve under the pressure of a single observation that the old framework cannot absorb. The history of science is not a story of steady accumulation. It is a story of thresholds, long plateaus of consensus interrupted by vertical drops into entirely new conceptual terrain, where the maps that worked before suddenly describe a country that no longer exists. Enceladus is a threshold. Not because it has already overturned the consensus. It has not yet, not formally. The data remains inconclusive in the precise, technical sense. Biology has not been confirmed. The methane anomaly has not been definitively attributed to living organisms. The scientific community has not issued a collective statement of discovery. All of that is true, and the distinction between what has been confirmed and what is being seriously considered matters enormously to the integrity of the process. But thresholds do not announce themselves at the moment of crossing. They are only visible in retrospect. From the other side, looking back at the moment when the last objection failed and the new reality became unavoidable. We are standing at that threshold now, on the near side, in the last interval of a debate whose conclusion is beginning to feel less like an open question and more like an approaching certainty. The Enceladus Orbilander. The proposed NASA mission concept. A spacecraft designed to orbit Enceladus for months before landing on its surface, collecting plume material, analyzing it for biosignatures with instruments an order of magnitude more sensitive than anything Cassini carried. The mission concept was formally assessed in the 2023-2032 Planetary Science Decadal Survey. The document produced every 10 years by the National Academies of Sciences, in which the scientific community ranks its exploration priorities and argues, in the most authoritative collective voice it can assemble, for where humanity should go next. The Decadal Survey listed an Enceladus life detection mission as one of the highest priority large mission concepts of the coming decade. That ranking is not ceremonial. It is the scientific community of the most powerful spacefaring nation on Earth saying, in language that budget committees understand, this question is important enough to spend billions of dollars answering. This question cannot be deferred another generation. This question, left open, represents an unacceptable gap in human knowledge about the nature of the universe we inhabit. The instruments being designed for such a mission are worth understanding in detail, because their specificity reveals exactly how seriously the possibility of life is being taken. Mass spectrometers capable of detecting individual amino acids, the molecular building blocks of proteins, compounds that on Earth are produced almost exclusively by living organisms or by the chemistry that immediately precedes life. Fluorescence microscopes designed to image individual cells, to distinguish between organic particles and actual biological structures with membranes and internal organization. Isotopic analyzers that can detect the specific carbon-12 to carbon-13 ratios that living systems produce. Because biology preferentially incorporates the lighter isotope in a pattern so consistent and so distinct from abiotic chemistry that its presence in a sample is considered one of the most reliable biosignatures known to science. These are not instruments designed to search for hints. They are instruments designed to answer a binary question with finality. And the fact that they are being built, that scientists are sitting in laboratories right now, designing the optical systems and the ion trap geometries and the sample handling protocols for a mission to a moon of Saturn, whose primary scientific objective is the detection of extraterrestrial life, is itself one of the most consequential facts of this century, regardless of what that mission ultimately finds. Because the building of those instruments is an act of belief, not religious belief, not the credulous acceptance of claims beyond evidence. Scientific belief, the reasoned conclusion drawn from available data that the probability of a positive result is high enough to justify the investment of resources, careers, and institutional credibility. Scientists do not spend decades designing life detection instruments for environments they privately consider sterile. The instruments are the argument, expressed in metal and glass and computational architecture rather than words. Now consider the second dimension of what comes after the impossible. The dimension that operates not in spacecraft budgets and instrument designs, but in the architecture of human meaning. If the Enceladus orbalander launches and reaches its target and descends through the plume material with its fluorescence microscopes and its amino acid analyzers and its isotopic sensors, and if those sensors return a positive result, the implications cascade outward from biology into philosophy with a velocity that no institution is currently prepared to manage. The confirmation of extraterrestrial life, even microbial life, even a single unambiguous cell, imaged beneath a microscope on a spacecraft 400 million miles from Earth, would be the most significant discovery in the history of human civilization, without meaningful competition. It would not be a scientific discovery that eventually filters into public consciousness the way most discoveries do, gradually abstracted by time and translation into textbook sentences that carry no visceral weight. It would arrive instantaneously, globally, in a media environment of total saturation, and it would demand interpretation from every framework of meaning that human beings have ever constructed. Every theology would face it simultaneously. Every secular philosophy, every political system that grounds its legitimacy in a particular account of human specialness or cosmic purpose. Every educational tradition that has taught children what life is and where it exists and why the question matters. The disruption would not be uniform. Some traditions have always held that the universe is vast and inhabited, that the divine or the natural is not so parochial as to have expressed itself only once, on one planet, in one corner of one galaxy. Those traditions would absorb the discovery with something approaching confirmation. Others, traditions built on frameworks in which Earth and its inhabitants occupy a unique and irreplaceable position in a cosmos otherwise empty of biology and consciousness. Those traditions would face a pressure of reinterpretation, for which no preparation exists. There is an analogy here that operates across centuries. When Copernicus removed Earth from the center of the solar system, the immediate reaction was not universal acceptance. The idea required generations to normalize. Not because the evidence was poor, but because the implications were too large to be held comfortably alongside existing frameworks of meaning. The heliocentric model did not merely change astronomy. It changed anthropology. It changed theology. It changed the relationship between humanity and its stories about itself in ways that are still being negotiated 500 years later. The confirmation of life on Enceladus would be heliocentrism multiplied by an order of magnitude that arithmetic cannot fully capture. Because Copernicus moved Earth from the center of the solar system to one point among several. The confirmation of a second genesis of life. Life that arose independently, on a different world, from different chemistry, under different conditions, would move Earth from the center of biology itself. It would transform life from a singular terrestrial phenomenon into a cosmic process, from an exception into a rule, from the most improbable miracle in a dead universe into the inevitable output of a universe that makes life the way stars make light. Routinely, abundantly, without particular concern for the philosophical comfort of the organisms it produces. That reframe, from exception to process, from miracle to mechanism, is not a diminishment. It is an expansion so total that the human mind, encountering it directly, tends to oscillate between awe and vertigo in a rhythm that feels almost biological, because the expansion does not make us less. It makes the universe more. It populates the darkness with the possibility of company. Not the company of radio signals and technological civilizations and the specific anxieties of contact, but something more fundamental. The company of shared chemistry, of convergent biology, of a universe in which the impulse toward life is not aberrant but elemental. And somewhere beneath the ice of a small pale moon, orbiting a ringed giant at the edge of the inner solar system, in an ocean that has never seen light, that possibility is not waiting to be created. It may already be living, quietly, completely, indifferent to the eons, exhaling methane into a dark sea the way it has always done, the way it will continue to do long after every instrument we have ever built has been consumed by time, until the moment, still approaching, when something we send across the void finally arrives, with eyes precise enough to see it. There is a question that science has always circled without ever landing on directly. Not the question of whether life exists elsewhere, not the question of what that life might look like, or how it metabolizes, or whether it carries the same molecular signatures that biology uses on Earth. Those are empirical questions, difficult, expensive, requiring spacecraft and decades and instruments of extraordinary precision, but answerable in principle, answerable by evidence, answerable by the kind of patient, disciplined investigation that science was built to perform. The question that science circles without landing is different. It is this: if we are not alone, if life is a cosmic process rather than a terrestrial accident, then what are we? Not biologically, not chemically, not in the technical vocabulary of astrobiology or planetary science, but in the deepest sense that human beings have ever used the word what to interrogate themselves. What is the meaning of consciousness? In a universe that produces consciousness the way it produces carbon, abundantly, inevitably, as a downstream consequence of physical laws that operate without preference or intention. What is the weight of a single human life? a single civilization, a single species. In a cosmos that may be quietly teeming with biology across distances so vast that contact is functionally impossible, even at the speed of light. These are not comfortable questions. They have no clean answers. And the discovery, or even the serious, evidence-grounded possibility of life on Enceladus does not resolve them. It detonates them. It takes questions that were once safely theoretical and makes them urgent in a way that philosophy alone, operating without the forcing function of empirical discovery, was never quite able to achieve. Enceladus forces the question into the present tense. The ocean beneath its ice is not a hypothetical. It is not a model or a projection or a thought experiment. It exists right now, at this moment, churning in the darkness of the outer solar system while you exist here, in the light, processing language, inhabiting a body that is itself the product of 4 billion years of unbroken biological continuity, stretching back to chemistry not fundamentally different from what may be occurring at the floor of an alien sea. You, and whatever might be living in that ocean, share a universe. You are made of the same atoms. Carbon forged in the cores of stars that died before the sun existed. Hydrogen that has been present since the first minutes after the Big Bang. Oxygen and nitrogen and phosphorus assembled by stellar nucleosynthesis across billions of years of cosmic time. The atoms in your body and the atoms in the ocean of Enceladus came from the same source events, were dispersed by the same supernovae, were gathered by the same gravitational processes into the same solar system, accreted into different bodies orbiting the same star, subjected to different conditions, and may have arrived independently at the same improbable, extraordinary solution to the thermodynamic problem of maintaining organized complexity in a universe that relentlessly tends toward disorder. Life on Earth, and possibly on Enceladus, is matter that learned to resist entropy, temporarily, locally, at enormous ongoing cost, but persistently, with a tenacity that viewed across geological time looks less like fragility and more like inevitability. Life clings. Life spreads. Life fills every crack in every habitable surface it encounters and modifies its environment to create new surfaces and new cracks, perpetuating itself forward through time, with a momentum that the second law of thermodynamics seems, paradoxically, to be unable to fully suppress. That tenacity is what the methane anomaly in Enceladus's plumes is quietly suggesting. Not intelligence, not civilization, not anything that would recognize itself in the mirror of human consciousness or respond to a signal or build a structure visible from space. Something far more ancient and far more fundamental. The basic, cellular, metabolic stubbornness of biology. The refusal of organized chemistry to stop organizing, the conversion of hydrogen and carbon dioxide into methane and water, and the energy to keep doing it again and again and again for potentially billions of years, in an ocean sealed from the universe outside it. Following the same logic that the first living things on Earth followed before the atmosphere contained oxygen, before the continents had fully formed, before the evolutionary lineage that would eventually produce eyes and nervous systems and the capacity to ask questions about distant moons had even begun. The very ancientness of what might exist on Enceladus is part of what makes it so philosophically vertiginous. If methanogens, or something metabolically analogous to methanogens, are living in that ocean, they are not primitive in the diminutive sense that word sometimes carries in casual usage. They are ancient, which is an entirely different thing. Ancient means tested. Ancient means successful across timescales that dwarf the entire history of complex life on Earth. The methanogens in Earth's deep subsurface have not evolved dramatically in billions of years because they do not need to. Their metabolic strategy is so efficient, so elegantly matched to the available chemistry of their environment, that the pressure to change has been minimal. They found a solution and held it. Whatever holds that same solution in the ocean of Enceladus has had the same opportunity. And if it has held it, if biology on another world has been quietly, persistently, successfully metabolizing in the darkness for as long as Earth has had life at all, then the universe is not what the silence suggested. The silence of the cosmos, the absence of signals, the emptiness of every radio frequency we have ever monitored with the hope of hearing another voice. That silence is not evidence of sterility. It is evidence that life, in its most durable and most common form, does not broadcast. It does not build telescopes or transmit signals or develop the technological ambitions of a civilization that looks outward. It eats hydrogen. It exhales methane. It persists without commentary, below the surface, in the dark, for billions of years. Most life in the universe, if life is as common as Enceladus suggests it might be, is probably like this: silent, microbial, unreachable by any communication technology we possess or can imagine possessing, present in the darkness of sealed oceans, on frozen moons, around gas giants, around stars we will never visit. Metabolizing in configurations we have barely begun to catalog, even on our own planet. Filling habitable niches across a galaxy of 400 billion stars with a biological quiet that will never resolve into a signal, never announce itself, never answer, and yet present. The loneliness that this picture produces is not the loneliness of an empty universe. It is a stranger, more specific loneliness. The loneliness of a universe full of life that cannot speak. Orbiting stars too far to reach, in oceans too deep to sample. Separated from us by distances and environments and biological scales that make contact, in any meaningful sense, effectively impossible. We are surrounded, potentially, by life we will never know. That is the emotional core of what Enceladus has placed in front of us, not the terror of alien contact, not the competitive anxiety of a universe populated by civilizations more advanced than ours, but the more intimate, more human grief of proximity without connection, of knowing that something exists across an unbridgeable distance and being unable to reach it, to speak to it, to confirm in any direct way that the longing for company that defines so much of human culture and human history and human science is not entirely asymmetrical. The greatest discovery in human history may ultimately be this: that we are not alone, and that it changes almost nothing about the practical texture of daily existence on Earth, and everything about the context in which that existence occurs. Everything about the story we are living inside. Enceladus is not the end of that story. It is the moment in the story when the protagonist realizes, for the first time, the true scale of the world they inhabit, when the walls of the familiar expand outward without warning, and the space beyond them is revealed to be not empty, but inhabited, not dead, but alive, not silent because there is nothing there, but silent because what is there does not yet know we are listening. We sent a spacecraft across 1.5 billion kilometers of cold vacuum and flew it through the breath of an alien ocean, and analyzed what it found, and rechecked the instruments, and published the papers, and argued about the methane, and decided, finally, that the question was important enough to spend whatever it takes to answer it directly. That decision, quiet, expensive, uncertain of outcome, motivated by nothing more practical than the human need to know, is itself a kind of answer. It says that consciousness, wherever it emerges, turns outward. That awareness, given sufficient time and resources, and the peculiar stubborn curiosity that seems to accompany intelligence, eventually looks up from its own ocean, peers into the darkness beyond its own horizon, and asks the only question that has ever truly mattered. Is anyone else out there? Enceladus is the universe's most careful, most qualified, most scientifically grounded whisper of a response. Not yet confirmed, but no longer impossible to imagine as yes.